Hi, so I'm Nathan Bronson. I'm from Facebook, and I'm going to talk about how we balance multi-tenancy and failure isolation, which are usually kind of contradictory goals in one of our high-volume data systems. So as you know, Facebook likes to move fast. We iterate rapidly. We try to fix problems as soon as possible. We push all of our business logic at least twice a day. We actually also rapidly change our data schema. So at the end of the year, we have a couple thousand new active node and edge types in the social graph that we didn't have before, on average a couple a day. So one way you can build a system, a data system, is to you have your application layer, and then you have data services that store different data types. So maybe we'd build a system that had a set of machines for storing users, a different set of machines for storing likes, and then maybe posts and comments on a different backend. This would be what I would call a single tenant system, where we had different products on different backends. We've chosen instead to build a multi-tenant system where we put all of the different nodes and edge types of the social graph go into a single set of machines. So you have a single database shard. We'll be holding users, it holds nodes, it holds likes, it holds the fact that you bought a tractor on Farmville 4 years ago. It's all stored in one place. The caches are also multi-tenant. So this gives us a lot of advantages. It means that we have minimal upfront design necessary. Like if we want to link a new data type to an existing node, a node type, there's no problem. We don't have to plan ahead in terms of how many machines are going to be necessary to deploy a product. It's very scalable in the number of data types. So if we try out something and it doesn't tend to work, we don't have like a lot of detritus left over in the configuration. And it also importantly allows us to very instantaneously redistribute capacity. So we have this, because it's a single system, it has a lot of excess capacity, and we can redistribute that to whatever the current problem of the day is. So if we do a viral launch and we haven't optimized our query patterns, we have enough excess capacity for any particular one problem at a time or a couple problems at a time, as long as we get the fires fixed before we move on to the next one. So we get a lot of advantages, but we basically are putting all of our eggs in one basket. So if something does go wrong, if we have an overload in the system or a capacity problem, it affects all of Facebook instead of just one part of it. So when I say isolation, what I mean is we'd like to have all the advantages of having just a single set of software, a single set of servers and hardware and capacity. But when it comes down to failures or slowdowns, we want those to be at a small granularity. So if it's a single data type, and it shouldn't be able to observe the fact that some other data type is having a problematic request pattern or something like that. So the strategy that we used is we basically started with multi-tenancy, and then we add in as much isolation as we can. Multi-tenancy is required in our system because of the scale, and isolation is something that we can add in as much as possible. So in order to dig into to how we provide isolation, I need to talk a little bit more about the like why we lose isolation in a multi-tenant system. And then once I do that, then I'm going to describe some of the principles that we use when we queue work into the system in order to keep the failure isolation from happening, or sorry, keep isolation boundaries from being broken. So if you look in our system, we have an application layer, which is stateless, and then we have several layers of stateful services. If your system was smaller than this, you might only have one level of cache, but you're still going to essentially have an application layer where any machine can access any data, and then you're going to have stateful layers of the system where you look at the ID of the data you're accessing, the key, and then you have some sort of a mapping that tells you which machine is actually responsible for holding that data. So in this case, a single machine in the level 1 cache, level 2 cache, and database holds a particular node or edge. Different data types, or sorry, different data items also all have a similar mapping. But so even though we're using a similar mapping function at all the different layers of the system, because these different services are different size, the actual like what objects are co-located tends to be different at different layers of the system. So for example, the pink and the purple, or sorry, the pink and the green are not co-located at the level 1, but they are co-located at the level 2 cache. And then on the databases, they happen to be independent again. So as requests go from the left side of this picture to the right side of this picture, at each level of the cache, we serve a lot of the requests, and we only send some of them on. So there's billions of queries per second going from the application layer to the level 1 cache. and then maybe 10% of those make it to level 2 cache, and then fewer of those make it to the database. So because we have this various different mixing and co-location, what can end up happening is that if we have a slowdown or problem in the system, it can end up affecting, the problem can be magnified and amplified at each layer of the system. So for example, a database that's overloaded, or maybe there's network congestion on a single database, might affect multiple machines at the level 2 cache. And then by the time we get to the level 1 cache, we've actually have a cascading slowdown that affects, or that would affect almost all users of Facebook in this particular cluster. So that would be a big problem. Because we have a large number of queries coming into the system, and then a small number of queries at the actual source of the problem, the interesting way to look at this, or when you're trying to diagnose the problem, is where's all the work getting queued up? Where is the congestion? An analog of this you get, like, if you're driving along and there might be an accident 10 miles down the road. It doesn't matter whether or not you're going to drive by the accident. Even if you're going to get off at the next exit, if you're not moving, you're still affected by the problem. So the question is, where is the queuing happening? And most of the backlog lives inside the cache machines in the middle. So we'll drill into that. So the architecture of a single cache machine, we have a high-performance I/O thread. So an individual cache machine does hundreds of thousands or maybe up to 1 million queries per second. So the cache hits are very fast. They're on the order of microseconds. There's not really any queuing. There's no backlog there because we can immediately get them, send them back out. On the other hand, if it's a cache miss, then we have to go to a different machine, or if it's in the case of a write, we might actually even have to go to a different data center or a different region in the country. For our European data center, this is even a transatlantic call. So we have a limited capacity, a limited number of concurrent work contexts that we can work for these remote contexts. So we can't do them at, the ingest rate might be higher than the maximum number of concurrent workers that we can have for these slow requests. So we have a queue. The queue basically lets us handle spikes. So these slow requests are on the order of milliseconds, and we can do a few thousand of them at a time. So when we have a backlog in the system, when we have a cascading failure, the work backlog ends up being in this queue. So most of the pending requests in the system are in the queue between what we call a fast thread and a slow thread. So this queue is, that's kind of convenient because we wrote the queue, so we have access to what's in it, and we can change the queuing policies and that kind of stuff. Over the years, we've developed a set of principles that we use for how we manage the work items in this queue in order to provide good failure isolation for the system, for the system as a whole, not just each cache machine. So the first principle that we have for how to provide isolation in a multi-tenant high-performance work queue is to fail quickly. So what I mean by this is there's two possible reasons why you might have a lot of work queued in the system. So one of them is that you've just received a big spike of requests, like 100,000 requests all came in simultaneously, but the system is generally healthy. So you had to queue up all the requests, but it won't be very long before you can finish processing the queue. So what ends up happening is that we have a big spike in arrivals. The queue length, the amount of things buffered in the queue, spikes up, but then we rapidly make progress on it, and the queue length drops back down to be very low. So the latency of the work items that we're dealing with, it's low until we have the spike, and then it kind of gradually rises as we work through the queue, and then once we finish working through the queue, then it gets back down to nothing. The other possibility is that the system is in a persistent overload scenario. So if we're receiving requests at a faster rate than we can actually process them, then the queue will become arbitrarily long, or however long we let it. If you're building a system like this with an infinite queue, you're going to have an infinitely big problem. And then everything that goes through the queue has a high latency. So even the successes that we have, even the requests that we get around to processing, will have a high latency. And this is a bad thing. So we want to avoid this lower right-hand corner. So the way that we do this, we were actually inspired by TCP's CODL work. And the inspiration is that, or the insight is that if you track how long it takes things to get through the queue, if you're in a healthy state, then relatively often something will make it through the queue pretty quickly. So obviously, depending on the performance of your system, like what not too long a time or what a long time is, that you have to figure out what those are yourself. But so in our case, like if within the last second we've been able to basically drain the queue, then we consider ourselves to be in a good state. So if you differentiate the fact that you're in a spike from the fact that you're in an overload condition, then you can deal with those two situations differently. You don't want to have a low queue timeout in a spike, because then you're going to fail a bunch of requests that you could have succeeded. But you do want to have a low timeout if you're in an overload, because you're not going to finish all the requests and you might as well immediately reply. So the second principle is to not fail requests that can succeed. So I guess there's a trope in finance that basically says the two rules for succeeding in finance. One of them is to not panic, and the other is to panic first. So I guess rule number one is panic first, and the second rule is to don't panic. So hard limits in this situation are bad. So a common approach to trying to provide good quality of service is to have some sort of a guarantee, like product X is allowed to request 10 million queries per second guaranteed. And if they request 11 million, then you reject the last 1 million of those requests. Or hard limits can also come where you try to avoid overloading your upstream by throttling your requests. So for example, if we guess that a MySQL server can handle a particular miss rate, and our miss rate is too high, then maybe we would throttle those requests and try to fail them. We tried pretty hard to make this work, and we were unable to get it to work at scale and reliably. And there were a few reasons. So the hard limit, if you set it too low, then you've basically created a bunch of failures out of thin air. So if you underestimate the capacity of your SQL server, then it doesn't matter what its real capacity is, like it's actually operating at the lower capacity. On the other hand, if you set the limit too high, then your limits have no effect. You might as well have just not had them. So there's a lot of like fine tuning and hand tuning that were required. It was difficult to keep it working well. And then there's also the problem of misclassification. So if you don't actually put something in the right failure bucket, then there's no chance that you can get the limits correct. There's a deeper philosophical reason here as well, which is there's actually a person at the end of the request. The reason why we're getting too many requests at some internal server inside Facebook is because there's a person using Facebook. So it's a pretty expensive way for us to communicate to a different product team inside Facebook that they need to optimize their queries if we fail the requests, because it actually impacts somebody's end user experience. So what we would like to do is we'd like to have a system where we can serve all the requests if we can. Like if we actually have capacity, it doesn't matter whether somebody has miscoded something and they have a very inefficient query stream. We should still try to render Facebook. And then we can follow up out of band. We can walk over to their desk or send an email. We actually have a team whose sole responsibility it is to like kind of continually track down these performance regressions. So what we'd really like is, instead of having a hard response, we want the ability to have a soft response. So actually this slide, like saying a soft response to a bad request is not even really the right thing, because at our layer of the system, we're basically dealing in heuristics and incomplete information. So what we want is a soft response to a heuristically suspicious request. So the queue gives us a couple possibilities. We can change the order in which things go through the queue. So for example, we can have more than one queue level, priority level. We can re-queue things if we decide we don't want to work on them at the moment. As long as there's enough capacity to service everything in the queue, changing the queue delivery order doesn't actually change whether or not you do the work, because you process everything. But then once you run out of capacity, altering the delivery order tends to push the failures onto the things that got put at a lower priority in the queue. We can also adjust the timeouts of the items that are in the queue. So for example, if regular requests get a longer timeout than your suspect requests, then once the timeouts start getting hit, then the errors will preferentially go towards the requests that have been given a lower or a flagged as potentially suspicious. And then the last thing we can do is we can limit the worker pool footprint for requests that we think are in error. So we can essentially reserve a portion of the machine always available for things that we consider to be not malicious or not heuristically suspect. So the last principle is to fail the right requests. So let's say that you're trying to debug a complicated distributed system. Something's not working right. The first thing that you do is you dig in and you try to figure out what the common feature of the problem is. There's a bunch of requests that are failing. What's the common factor? Sometimes the factor is who is making the request. So for example, we might have had a product launch that went better than expected, or maybe it's a new workload that hasn't optimized their query pattern. So the common factor is the source of the requests. This could also be like a batch job that was launched that was a bit too aggressive. One common divisor of a problem is the data that's actually being read or written. So we could call this a hotspot. So it could be a hot shard. It could be something that's being written very heavily. It could also be a particular data item that for some reason has like an uncacheable, like maybe it exceeds the size of one of the cache. There's too many edges, and so we can't fit them all in cache or something like that. The third possible thing is that the common factor is where we're going to have to go in order to serve the query upstream. So for example, there might be a bunch of machines in the L2 cache layer that all are going to talk to the same database. And if the requests that are failing are all about, or all the ones coming just from that particular database, then the data destination is the common factor between all the problems. So we're not really talking about buckets anymore. Like if you try to bucketize by all of these things at once, you're going to end up with like a bunch of buckets for who, a bunch of buckets for what, a bunch of buckets for where. You do the cross product and you end up with tiny buckets that are not very useful. We're actually talking about something that looks more kind of like a machine learning classification style thing. We have a bunch of features of a request, and we want to make a decision about whether or not something is suspicious based on those features. So I'm going to tell you the strategy that we adopted. It's probably not the only one, but it works pretty well, and it's implementable at very high performance. So if you look at the details of a request, we have a lot of pieces of information attached to the request. And these basically corresponds to the failure domains that I was talking about before. So when the requests come into the system, they're annotated with the application that sent it in. This might be an ID that identifies, for example, like the iPhone app, or it could be a website for a particular product. And we also know the machines that a request has traversed on its way in. We know what data is being accessed, obviously, because that's what you have to send with a request in order to be able to answer it. And we also, at this point, have a guess of where we're going to have to go next in order to serve the request. So we can take all of these different various types of things, and we can compute a bunch of, we call them tags. So these range from things that are very generic. So for example, the op-get tag that's kind of in the middle, like that just means we're doing a read. So the cache is mostly doing reads, so almost everything gets that tag. It's a pretty generic tag. That tag might be useful if we're trying to, for example, guarantee that we still preserve the ability to do writes, even if the reads get overloaded. And then there's also tags that are very specific. So this is identifying a single node in the graph. That could be a failure domain. Maybe this is like Justin Bieber has just uploaded some new photos or something. So we have his ID. So once we have all of these tags, then we keep track of what fraction of the machine capacity we're actually devoting to requests with these tags. We call this the scoreboard. So for example, if a request comes in that has these three tags, while the request is being run in the worker pool, we have a single per server scoreboard that keeps track of the sum of the tags. So this is a multi-set. And then once we've summed up all of the things, we'll notice, like in this particular example, we have 3/4 of the machine capacity is being devoted to a single edge type. So that sounds a little bit suspicious. Like we would kind of expect there to be a better distribution. So what we'll do is we'll set a threshold and say, well, if this particular tag is above a particular count, then we think of that as suspicious. If a new request is about to be executed, we check the scoreboard and we compare it to the tags that are in the request, and then we see whether or not it shares any suspicious tags with the scoreboard. So this top request is fine. The bottom request is also for edge type 7, so we're going to consider this to be a suspicious request, and we're going to treat it differently. So our new workflow looks something like this. This is inside a cache machine. If a request comes in, if it's a cache hit, we go ahead and service it immediately. It turns out the cost of sending back an error failure message is actually almost the same as sending back the response, so there's not really any point, in this system at least, of trying to do queue management for the hits. We put it into a queue, the same as before, and then once it's traversed the queue, once we're about to execute it in the worker pool, we check to see whether or not any of the tags are suspicious in the scoreboard. If everything checks out okay, then we run it in the worker pool as before. We go off box and then we send the response back. So while it's executing in the worker pool, we add all the tags into the scoreboard. So the interesting thing happens when a tag is over the limit in the scoreboard, we re-queue it into what we call a low priority queue. So if the worker pool doesn't find anything at all in the default queue, then it goes and looks in the low priority queue. So once the system, if the system is operating below capacity, we're still going to process all the low priority requests. If the system is out of capacity, then things sit in the low priority queue and don't actually get serviced. So after they've been in there for a while, I think it's a 10 millisecond timeout, then we basically like pull it out of the queue early and send it back to the client and tell them that we're overloaded and they should go somewhere else or give up. So you'll notice a couple interesting things about this. So the first intuition here might be to put it into a default priority queue or a low priority queue using the scoreboard before, like to make the decision before it's actually traversed the queue once. So the reason why we make the decision as late as possible is that this is basically a control system with a feedback loop. So by making the decision as late as possible, we keep the feedback loop as tight as possible, and it minimizes the chance of oscillation. Another thing you'll notice is that we actually only keep track of the tags of things that are in the worker pool itself. We don't sum the tags of things that are in the queue. And the intuition here is that we're trying to track the fraction of the machine that is actually being devoted to a particular set of tags. So our queue is very high performance. We can put millions of things through it per second. We can time out millions of things per second from the queue. So the fact that something is in the queue is taking up only an epsilon of the machine resources. The main machine resources that we're talking about are the worker pool contexts themselves. So if you had a system that was like this and the queue was more expensive and the worker pool was less expensive, then you might choose a different strategy for that. We also have, I didn't put it on here because it would make the slide really busy, but we actually have more than one low priority queue depending on which tag it was. So we have a particular tag that is very indicative of something that's very low priority, and we give it like an even lower priority thing. So I've told you how the tags work, but I haven't told you how we choose tags or limits for tags. So I'd like to tell you that we have some super duper algorithm that does this all automatically. And the reality is I had a really good PhD intern, and we did some studies and did some deep analysis of the past failures of the system. So we were inspired here by epidemiology. So epidemiologists are trying to determine, they're trying to correlate the fact that people are sick to how you can tell that they're sick. So they have a tool called a case control study, where they get cases, people that are sick, and they get controls, people that are healthy, and then they have a bunch of features or indicators of that. So if they're doing a genetic analysis, then their features is basically the set of all genes that they've studied from you. So that's what we did. We took a bunch of servers that were clearly unhealthy, and then we took a subset of samples from servers that were clearly healthy. And then for any particular algorithm that computes a tag, you can build a little matrix, like how often was the tag over limit and the server was unhealthy versus healthy. And then if you plug all this into Bayes rule, you get you can compute a probability that a particular feature tells you that the server is unhealthy. So now that you have this probability, you can evaluate a bunch of different limits and a bunch of different tag generation algorithms, and you can pick the ones that are right. So in this case, we chose the ones that had the best impact, and we hard-coded them because we're trying to do this at very high performance. There's a little bit of a catch-22 here, which is that once you put good tag functions and limits into the system, then the system gets healthier, so it becomes harder to gather new cases and controls. So we don't have a good answer for that yet. I guess we can always just turn it off for a couple days and get some more good data, and then we'll turn it back on again. So this graph shows 1 year of capacity errors for the system that I'm talking about, the tau system. So we deployed this kind of in a staged rollout at the middle of this. So you can see a couple things here. The background failure rate, the failure rate when there wasn't like a spike of errors, dropped from something that was, I mean, there's no units here because of legal review, but the failure rate before was non-zero. It was actually pretty low, but we were able to get it almost all the way to zero. So this is basically the don't fail request that can succeed effect. The fact that we're trying to always satisfy requests whenever we can means that when the system is in a normal scenario, we don't fail any requests at all. Then the second thing you'll notice is that when there was actually a problem in the system, and this is basically a spike. So a spike here could have been some sort of hardware failure in our network. It could have been a bad code push that had a bad query pattern. The height of the spikes has come down a lot. And so the height of the spike is basically this is the effect of the tag system. So once something does go wrong, then the tags wall it off and prevent it from causing the rest of the system to not work well. So to recap, we need to fail quickly. This helps us keep the latency low even during overload. We need to make sure that we don't fail requests that could succeed in order to keep our baseline failures low. So we do this by having soft responses instead of hard responses to failure. We don't try to introduce new failures into the system. We just try to rearrange the ones that are already there. And we want to make sure that we suspect the right symptom or we fail the right requests. And this helps us avoid amplifying the failure spikes. So once in the multidimensional space of tags, if we can find a tag that correlates with the failure, then we can isolate the failure just to that particular tag. And the result of this was quite successful, and we've actually been running it for a couple years now. So I think we're out of time, so there might not be any questions now, but I'll be outside in the office hours afterwards. Thank you very much.
Yeah, thanks, Nathan.